Thank you, Staju. Great talk. After listening to two presentations about storage systems, we will move a little bit up to the stack to talk about data processing systems. Batch analytics and streaming processing traditionally are two different scenarios, require different solutions. As our final presentation, Yuan from Alibaba will talk about the evolution of stream batch unification in Flink, which has been used to support one of the largest e-commerce events in the world. Let's welcome Yuan.
Hello everyone, this is Yuan, saying hello from Beijing office Alibaba. I'm from the real-time computation team Alibaba. Before joining it, I worked in the Facebook data infrastructure division. I'm quite excited to have the chance to come back and share the talk here. So, in 2018, at the same scale conference, Xiaowei from Alibaba was invited to share the best practices and the challenges we solved to scale Alibaba's real-time infrastructure for Double 11. That is to support the world's largest shopping festival on world's largest e-commerce platform. For people who are not familiar with the Double 11 shopping festival, well, the event is similar to the Black Friday in the US. Every year on November 11th, almost all products are on sale with the biggest discount over a year. Most of them have an extra discount for the first few hours and just after midnight. So you can see that from a provider and the platform perspective, we would enter the highest traffic over the year. Well, the number of activities and the transactions will be multiple times higher than during a normal day. Then it is natural to ask how things go after 2018. What are the other new challenges we are facing and how we are solving them? Well, these are exactly I'm going to talk today. So the GMV of Double 11 is growing steadily each year. In 2020, it reaches 74 billion US dollars with more than 800 million participant consumers. At peak, 583,000 orders are created per second. The GMV value, along with many other indexes, are updated in real time when a new order or event occurs. These updates are displayed through a GMV dashboard to the general public, as shown in the colorful screen on the left. Flink is used to clean, join, and calculate such value underneath. The end-to-end latency shown here is controlled within 1 second. Let's take a look at some numbers. In 2020, during Double 11, the peak processing rate for real-time computation reaches 4 billion records per second. Well, remember, the number in 2017 is 470 million events per second. That says it's nearly 10 times improvement in 3 years. The data volume reaches 7 gigabytes per second. That's roughly equivalent to process 5 million Xinhua dictionaries per second. Xinhua dictionary is a standard character dictionary in China, similar to Webster's dictionary in the US. The end-to-end latency on average is within sub-second. The total number of real-time pipelines is more than 35,000 with a total CPU cores equal to 1.5 million. While in Alibaba, we use Flink as real-time computation engine. Flink is Flink plus improvement to support data processing in large scale, as mentioned in Xiaowei's talk in 2018. But after Alibaba donated Flink back to the Apache Flink community in Flink version 1.10, we do not differentiate Flink and the Flink that much internally. So in this talk, I will just use Flink. Well, this timeline shows how Flink or Flink grows in Alibaba. Flink is an open source project and was recognized as Apache top-level project at the end of 2014. Alibaba is amongst one of the first enterprises that choose and use Flink in its core business in large scale. And Alibaba made big efforts to improve Flink's scalability and high availability. In 2018, Alibaba Cloud launched a real-time computing product based on Flink to provide cloud computing services for small and medium-sized enterprises. In early 2019, Alibaba acquired Flink's founding company and began to invest more resources in Flink ecosystem and community. One of such big efforts is to merge Flink back to Flink. Well, now Flink has become a de facto standard for real-time computing in the big data industry. Well, you can see that the Flink community grows rapidly and steadily after Alibaba's acquisition. According to Apache annual report last fiscal year, Flink is one of the most active open source projects, with top 1 dev and user mailing list activities, top 2 number of commits, and GitHub visits. In addition to improving Flink's capability for real-time processing, there are also other interesting work ongoing, like stream batch unification in Flink. Flink is not just the streaming. Well, this comes to our main topic today, stream and batch unification in Flink. During last year's Double 11, the Flink-based stream batch unification pipelines were used in the core market decision-making system of Tmall for the very first time and achieved remarkable results. I will show you the results in the end. Just wait for a second. Well, such decision-making systems typically offer 2 types of data reports. One is the incremental real-time reports, and the other is the batch offline reports. But the incremental real-time reports help to make timely decisions for sales promotion, for example, and the offline reports provide historical results for comparison and also works as a backup pipeline and verifies incremental reports. And such system is traditionally achieved by a typical Lambda architecture, as sketched in the graph, that incremental processing and batch processing use typically 2 different systems. Well, you can almost immediately find there are some problems in this architecture because the similar logic is developed twice in 2 different systems, and we have to maintain 2 pipelines in 2 systems that almost do the same thing. And most importantly, you cannot guarantee consistent analysis results because they are using 2 different systems. And when such inconsistency occurs, it is extremely difficult to reason about and debug. Well, if you ever worked with such system, you know what I'm talking about. So it seems something can be unified here. That is so-called stream batch unification. Stream batch unification has been talked for a few years already. If you talk with people from different backgrounds and companies, they will view this concept in more or less different ways. If you start with the batch system, you probably would think to accelerate your batch pipelines using mini batch. But of course, the end-to-end latency is not that good. Or if you already have both a stream and a batch system in your data infrastructure, you probably think to unify the API level and generate different physical plans for different underlying systems. That's the most convenient way to do. Or like what Flink does, unify in all system levels. I will dive into detail in just 1 minute, but before that, I want to highlight something that's, I think, really important. A stream system was treated as a second-class citizen before Flink emerged. What does that mean? We know that one of the core characteristics of Flink is it can guarantee exact one semantics. Before Flink, people do not trust the results generated by stream processing. They have such Lambda architecture that has one stream pipeline generating low latency incremental results and always have another batch pipeline for calibration. Flink's light-weighted snapshot algorithm guarantees exact one self-contained consistent semantics, making stream processing a first-class citizen that we do not rely on batch pipelines for correctness anymore. This is the foundation that we can make possible batch processing a special case of stream processing in Flink. And the exact one semantics guarantee is also the foundation of stream batch unification in Flink. Well, now let's come back. Think about what's the goal that we want to achieve for stream batch unification. Comparing against the traditional Lambda architecture, so these are the goals that we want to achieve. Reuse code and logic across real-time and historic data processing so that users do not need to write duplicate logic for 2 pipelines. Consistent semantics so that complexities are hidden underneath. Then users do not need to learn 2 sets of languages or APIs. Unified operators and runtime so that we do not need to maintain 2 different systems. Mixing real-time and historical data processing so that we can do, for example, backfill seamlessly. How we achieve these goals in Flink? Then let me start with probably introducing 2 important concepts in Flink, which relates to fundamental differences between stream and batch data completeness and the latency SLAs. For stream processing, Input data keeps coming and does not have an end, while in batch processing, data is complete before processing them. This difference is expressed as unbounded versus bounded input in Flink, as shown in the graph. Bounded can be viewed as a subset of unbounded. The other difference is latency SLAs. Streaming job has SLA requirements, so it processes as input data comes in and it generates incremental results. While batch processing does not have such requirements, it only needs to generate final results after all input data complete processing. So this leads to execution mode in Flink, stream versus batch. While stream supports increment updates, while batch is done in just one shot. From these 2 points, you can see batch processing is actually a special case of stream processing. Well, logically, yes, but physically, not exactly. They are different in APIs, which are used to build a DAG, with a bunch of different operators, with different runtime support requirements, and different ways of scheduling and failure handling. Flink supports 2 types of APIs, declarative relational SQL table API and the imperative data stream API. They are unified in expressing stream batch applications. One is in a higher level, declarative, and you can apply optimization on it. And the other is lower level, imperative. They can be mixed and converted within the same pipeline or application. The main difference to express stream and batch application is about time. Time is a very important concept for unbounded data stream in the sense that it decides the order between events based on time. It is also important to stream or incremental processing to decide when to trigger the incremental output. Watermark is the element in the stream to tell us the progress of the time. In stream mode, you cannot simply use the machine time or ingestion time to decide the time progress because in time input stream can be significantly delayed. For example, our sensor on mobile uploads its data whenever it has free connections, so the delay is unpredictable. We need a time marker to measure the relative order and the relative time between elements in the stream, which is watermark. We use watermark to decide whether arrived data is late or not and how late data is handled. Should we just ignore it or need to do retraction instead? That is actually quite complicated. On the other hand, time does not matter that much for bounded dataset because data is complete. We know when it starts, when it ends, and only final results are reported. Logically, you have watermark minus infinity before processing, and once all the bounded data are processed, the watermark is immediately jumps to the plus infinity. This way, you never need to worry about the late data in batch execution mode, and this is how we unify watermark handling for stream and batch in Flink. The second difference lies between stream batch is handling stateful operators. In stream mode, stateful operators like aggregations or joins, its operator state is kept in the state table. As new data comes in, the new data is processed and the state table is updated accordingly. As shown here. The corresponding count in the table is increased by 1 and output the newly updated results. Well, this becomes complicated and costly if the state is large and cannot be kept in the memory, and there are also a lot of overhead because of the state table accesses. Well, in the batch mode, things are much simpler. Input is bounded, so we can just sort the data and do the group counting and send the result to downstream just once. In this case, we do not need to worry about large states because the data is sorted and we do not need to maintain states for different keys at the same time. And correspondingly, we do not have a huge number of state table access as well. We have a unified stateful operator for both stream and batch processing. Just add a sort of input in the batch mode, like this, shown in the slide. The third difference lies in how data is transferred between operators. In the stream execution mode, upstream and downstream tasks are connected through pipeline shuffle. The upstream sends results to downstream as soon as they are available. To keep short end-to-end latency, of course, states are kept and updated as new input comes in. The stream job has to be always running because the input data is unbounded. Hence, it needs to periodically do the checkpointing, where consistent snapshot of state table is taken, so that when failure happens, the operator can restore the state table from the snapshot. This is aforementioned how we can guarantee exactly one semantics in Flink. In batch mode, since latency is not a strict requirement, tasks can be connected through the blocking shuffle. That means tasks that execute the operator exit after finish, and we can execute the operator one after the other. The output is materialized until the entire job finishes. In this case, there is no need for checkpointing. If there is a failure, execution can just backtrack to the latest available intermediate result. We provide a unified shuffle service API and make the shuffle service pluggable to fit into different data exchange modes. Currently, we have 3 types of shuffle service available in Alibaba. And the first one, built-in shuffle service managed by Flink Task Manager. This is also available in the open source version. Well, batch shuffle can work, but not in the best performance in this case, because it's optimized for the pipeline shuffle. The second one is Yuan shuffle service. Flink can integrate with shuffle service provided natively by the underlying class managing system like Yuan. The third one is remote shuffle service. In Alibaba, we've recently launched a new remote shuffle service that is optimized for batch shuffle. It is already launched internally, and we will soon release it publicly. And let's wait and see. The last difference lies in the workflow level that handles, for example, scheduling and failure. In the previous slide, we mentioned that the lifecycle and failure handling in stream batch mode are different. In stream mode, the job is not able to start processing until all the tasks are running. A task is a physical instance that executes an operator, or all tasks have to participate in checkpoint to make a complete snapshot so that we can do failure recovery based on it. In the batch mode, tasks can run one after the other as long as all the upstream data is available to execute the next task. Failure handling is done by backtracking, no need for checkpointing. Then how we unify them? We unify them through a concept called pipeline region. This is a full execution graph for the word counting example we showed before. It has 4 operators: source, key by partition, count, aggregation, and sync. Each operator has 2 parallelism. In stream mode, tasks are connected through pipeline exchanges. Well, you would expect in the batch execution mode, tasks are connected through blocking edges. Yes, but not all of them. As you can see, if you write everything in files, performance is bad. So we have different optimization policies to improve performance. In this case, we have the all-to-all connection in the middle set as blocking exchange, while the rest of the connections are kept as pipeline. This divides the execution graph into 4 regions as shown. Inside each region, tasks are connected through pipeline edges, and we make these pipeline regions as a unit for scheduling and failover. Pipeline regions are scheduled and running one after the other topologically, while tasks within the same region are scheduled all together. This is how we do the scheduling based on the pipeline region. While during failover, backtracking is done region by region as well, as long as its upstream data is still available. But in this case, if the counter task fails, we only need to rerun all the tasks in its pipeline region, as shown in the gray box. I've just illustrated what does stream batch unification mean in all system levels in Flink. But overall, we want to provide a consistent and a unified user experiences when they are writing no matter stream or batch jobs, and hide system complexities underneath. So user only needs to learn one API, write one logic, maintain one system, and they can get consistent results. But of course, along the way, we've done much more work than I just presented in these 20 minutes. Starting from Flink 1.11, so this actually shows some major milestones that we've achieved along the way. Targeting next release 1.14, which is 4 to 5 months after now, We are going to support hybrid resources and checkpoint after task finish to support mixing or switching between historical and real-time data processing. After this, the stream and batch unification story in Flink completes. Well, here's a link of Flink's roadmap about stream batch come together. There are some more details you can check, and also there's more plannings there. And if you're interested, you could take a look. Remember, at the beginning of the talk, I mentioned that during last year's Double 11, the Flink-based stream batch unification pipelines were used in the core market decision-making system of Tmall for the very first time. And we achieved remarkable results in different parts. Data consistency. This is actually the main reason that just a few months before Double 11, the data middleware team in Alibaba finally decided to switch batch pipeline to use Flink. Well, they made the right choice. The second one is the development efficiency improved 4 to 10 times. And it's also speed up the daily batch report by 4 hours after migrating to Flink batch. They save half of resources by collocating an off-peak execution. Batch execution, they could dump during the real-time traffic flow as shown in the scratches here. The other number that I want to share is Flink's batch execution performance. This is the aggregate time for TPC DS benchmark. With 10 terabyte data, 20 machines, each with 64 cores and 256 gigabyte memory. Well, the performance improved quite a lot, but the key message I want to deliver here is batch performance and the stability is improved significantly during the last 4 Flink releases. Now Flink batch is ready for production, and the performance is as good as any industry-level batch engine. Well, there were a lot in this talk. I've shared a lot. If there were anything that you would like to take away, here's a list. Flink is not just for streaming. Flink batch is ready for production already. Batch processing is a special case for stream processing. You can say that, but it's not that simple. Flink unifies stream batch unification in all system levels to make users just learn one API, write one logic, and maintain only one system. Overall, we want to provide a consistent and unified user experience when they're writing no matter stream or batch jobs and hide all the system complexities underneath. We provide us consistent semantics and the capabilities to switch between batch and stream execution in Flink. And last one, exactly one's consistency guarantee is a foundation for Flink stream batch unification story. This concludes the talk. Thank you everyone for your time. I hope you enjoy it and keep safe.